The title of my talk will be Why Splunk Chose Pulsar. So I'll go through a bunch of requirements that we analyzed and talk about why we chose Pulsar. So this is me. I'm the Senior Director of Engineering managing the Pulsar team at Splunk. Before Splunk got acquired I was the ex-CEO of Streamlio and co-creator of Twitter Heron. And I and Matteo and a bunch of others in the Pulsar community used to work with at Twitter also. And I have a PhD in computer science from University of Wisconsin-Madison. So these are forward-looking legal statements. So first, the agenda of the talk will be multiple bullet points. First is the introduction to Splunk. I'll give what Splunk does actually. Then I'll outline the requirements for a streaming system. And when you evaluated Pulsar, how it satisfies those requirements. And finally, I will conclude with how Apache Pulsar is being used at Splunk. So introduction to Splunk. So in the modern age, there is a lot of new technologies and are enabling and fueling digitization. The move to the cloud, then the faster 5G networks, and the sensors are plummeting in cost that you can now embed sensors in pretty much everything. Advances in AI, and so essentially the data being captured has increased tremendously. And so does the technologies to move data as well as analyze the data.
Hi, Karthik. Sorry to interrupt. I don't think that your screen is moving. We're still on the title slide.
Okay, so I'm not sure. Can you see my screen now?
Yes.
Only once I go into presentation mode, it becomes a little bit harder. So data is transforming everything the way we work, live, and play. Now I'm transitioning to the next slide. Do you see the change in slide?
We are still on the data is transforming everything slide.
Okay, I have no idea why it's doing that. So let me go through the presentation as it is rather than going in the presentation mode, if that is okay.
Yeah, that should work. We can give it a try. Otherwise, we can share on our side as well.
Okay. So that means like it says sharing is paused. Bring your window to the front.
We can see your screen. That looks great. It's just the challenge of moving from one slide to the next.
Your screen sharing. Okay, so let me see if I can.
If you click on the share screen at the bottom, which it looks like you've done, and then just click into the power. Is this a PowerPoint?
This is a keynote.
Okay. If you want, it's a little less pretty, but you can go ahead and continue in the current one that you were just in and just click down from slide to slide because we can still see the slides.
Okay, so let me do that. Okay, so where was I? I was in the number 6 slides. So data is transforming everything, the way we work, live, and play. So Splunk essentially provides a slew of products in order to capture the data, move the data, analyze the data, and distribute the data in the domain of IT, security, and DevOps, and enforcing business processes like compliance. So this is a short introduction to Splunk. Of course, Splunk is much more than a bunch of, several products. Now let us look at the core, what are the emerging use cases? I mean, we have seen in the field there has been a lot of ask about real-time monitoring and notifications, interactive applications, log processing and analytics, and data capture from IoT, and analyzing those data, data transformations and data enhancements, and real-time visibility into the data, and providing analytics and distributing the data that is continuously being captured, and event-driven workflows to structure how the event is processed as it flows through these workflows. So now when we look at all these emerging use cases, the core of these use cases is some kind of a messaging system or a streaming system. So hence the choice of the streaming system is very important in order to enable these use cases. And let us look at some of the requirements that we gathered for evaluating a very good streaming system. So the requirements are broadly classified into technical requirements, operational requirements, as well as business requirements. So I've not classified them explicitly, but I've indicated all the requirements here. So there is scalability, durability, fault tolerance, high availability, and sharing and isolation, client languages that we can program to interact with the system. What are the different type of messaging models, persistence, type safety, deployment in Kubernetes, operability of the system, disaster recovery, and the total cost of ownership, and how to observe the system when in production, and what kind of ecosystem the open source provides, and how much adoption has happened, then how much is the community, how active is the community, and what type of licensing. These are the various requirements that we evaluated at Splunk. So now I'm going to walk through each one of those requirements and how Pulsar satisfies those requirements, and if it close to satisfying, how we made it some implementation to fill in the gap. So the requirement one is scalability. The traffic can widely vary while the system is in production. System needs to scale up with no effect to publish and consume throughput and latency. That support for a linear increase and decrease in publish consume throughput as new nodes or new pods are being added into the system, and automatic spreading out the load to new machines as new nodes are added. Then, of course, we need a scalability across different dimensions like serving, compute, and storage. Now, how does this requirement satisfy? So Pulsar essentially has a multi-layer architecture that allows for independent scaling of processing, serving, and storage. And messaging and processing are built on top of Apache Pulsar, while the storage is built on top of Bookkeeper. And the worker is the third layer, which runs on top of broker, which allows it to do function processing or processing on top of data. So because of this individual capability, you can scale, you can start small, and you can scale it up as traffic increases, as more and more products and emerging and use cases are onboarded. That's the first requirement. The second requirement is durability. Splunk applications have different type of durability needs. One is persistent durability, no data loss in the presence of node failures or even inter-cluster failure. And this is needed in the case of applications like security and compliance. Then the second one is replicated durability, where no data loss in the presence of limited node failures. For example, when you do machine log processing, the logs needs to be replicated, but if the entire cluster is out, we can sustain some loss of logs. Then there is a transient durability, where data loss in the presence of failures is acceptable, especially in the form of metrics data. So now let us look at how Pulsar provides these various different durabilities. So the Pulsar, the data path looks like the following, where data is produced by producer, data is given to the broker, and the broker in turn replicates the data depending upon the number of replication, the replication factor, and the data goes into bookies, and the bookies in turn use journal in order to sync the data. Then the acknowledgement is generated from the bookies, which the broker collects the acknowledgements, and once the acknowledgement reaches a certain threshold, then the acknowledgement is provided to the producer. So because of the use of journal, we can have the persistent durability. The second type of durability is you can disable fsync, and we can just replicate the data and do a background sync of the data into the disk. That is replicated durability. So which means the durability is achieved by data replication rather than doing the journal. So when there is data is pushed into the journal, even if the entire cluster goes away, and as long as the disks are available and the cluster can be reconstructed, the data will be still available. Then the third one, transient durability. So that is provided as in the form of non-persistent topics, where the data is cached into the brokers and they never reaches the bookie, and it's served out of the broker itself. If the broker dies, then you will incur data loss. Now let us look at the fault tolerance. In the fault tolerance requirement, we need the ability of the system to function under component failures, and ideally without any manual intervention up to a certain degree. So Pulsar provides for inbuilt fault tolerance for handling broker failure as well as bookie failure. In the broker failure, topics are reassigned to available broker based on the load, and can construct the previous state consistently because the state is stored in bookkeeper, and no data needs to be copied. So which means broker increase and decrease as well as broker failover and coming up in some other node is very easy from an operation standpoint. The bookie failure, where the writes will switch to the node because the current segment will be closed and the new segment will open in the a different set of bookies, and they continue to the data writes continue to happen. Then the background process copies the segments to other bookies to keep up the replication factor. So Pulsar provides so these are all happens automatically without any manual intervention. The next requirement is high availability. So the system should continue to function in the cloud or on-prem in the following conditions if applicable. When two nodes or instances fail, when an availability zone in the cloud or a rack within an on-prem environment fails. So how this can be achieved? So node failures can be mapped into more of brokers and bookie failures that we covered in the earlier requirement, and it will be handled very similar to the respective component failures. Now, how do you handle zone and rack failures? So the bookies provide rack awareness in the form of labels. So then we can set the broker such a way that the data replica occurs on the bookies located in different racks. So when a rack fails or a zone fails, the data is available in the other zones. And this, because of this inbuilt capability in Pulsar, this satisfies this requirement. Requirement 5, sharing and isolation. Systems should have the capabilities to share many applications on the same cluster, especially from a cost and manageability standpoint, and isolate different applications on their own machines in the cluster when needed. So Pulsar provides inbuilt multi-tenancy in the form of tenants, namespaces, and topics. And by default, these some of the features like software isolation, where storage quotas, flow control, back pressure, and rate limiting can be done at the tenant and namespace level. Then hardware isolation, where you can constrain some tenants on a subset of bookies or brokers. You can isolate them when needed. So this is one of the must-have features in the system. And since multiple teams are used to different languages, so we need to have a first-class support for the client programming language, and that language support includes for Java, then C++, Python, Go, and C. So officially, all these language clients are officially supported project, which is a good thing. Then multiple messaging models. So Splunk applications have a different variety of consumption. One is type of consumption is collect once and delivery once capability. Example, sometimes we process S3 file and ingest into the index, and we have to inform that S3 file has been processed. But at any given one time, only one process or one worker needs to process the file. Well, the acknowledgement has to be provided once the processing is done, but it has to be given to only one worker. Then receive data once and deliver many times. This is in the case of Example is multiple pipelines sharing same data for different type of processing. So in this case, some pipelines might be going faster, some kind of pipelines might be going slower, but they all underlying share the same data. Then, people recommend having two different systems for these different capabilities for different consuming models. But we want to avoid two systems if possible, again, from a cost and operations perspective. Some discussion came up, hey, why can't we use one system and write a glue code to emulate possible that emulates the semantics on top of the other system. But again, that requires maintaining infrastructure code and continued cost of employing resources in order to keep up with that maintenance as open source changes underneath. So Pulsar supports, in order to satisfy this requirement, Pulsar support two messaging models, which is the messaging and the queuing, and in the form of subscriptions, exclusive subscription, failover subscription supported for messaging models, and the queuing models, shared subscription and key shared subscriptions provide the queuing consumption behavior. So the native supports avoid those systems and the extra infrastructure code that requires maintenance. Now the fifth requirement is persistence. So as the data gets older and older, we might want to offload it to, especially in a cloud-like environment, we want to offload to cheaper storage like S3. It can happen either manually or automatic and transparent to publishers and consumers. And we want near infinite retention because depending upon the applications like compliance versus security, these data might have to be stored near infinite for several months or even several years in order to satisfy the compliance requirements. So with the Pulsar providing the tiered offload, this requirement is satisfied. Then type safety. The Splunk applications are very varied. One class requires very rigid schema with no room for change. Another class requires some fixed schema with the capability for evolution. Other class requires flexibility for no schema at all, which are the schema to be handled at the application level. And of course, there are high metadata and other components, metadata components or data catalogs that we can bring in, but you would like to avoid bringing yet another system for just managing schema alone. And support for multiple different type of formats like Avro, JSON, protobufs, etc. was one of the requirements. So Pulsar Schema Registry provides the type safety applications built on top of Pulsar. It enforces server-side type safety and ensures that producers and consumers remain synced at all times. Schema Registry enables clients to upload their data schemas on a topic basis, and the schemas dictate which data types are recognized as valid for the topic. And there is a rich schema evolution as well in Pulsar. So this satisfies a type safety requirement. Then the requirement number 10, ease of deployment in Kubernetes. So Splunk heavily uses Kubernetes for orchestration. That's any system that is brought into Splunk for production needs to be easily deployable in Kubernetes. The surface area of the system exposed outside Kubernetes should be very minimal, like ideally like a single endpoint backed by a load balancer. Should be able to segregate the nodes receiving external traffic. If the system endpoints are exposed, those nodes should be separable from the core set of nodes and should be flexible to deploy from CI/CD pipelines for testing and development purposes. So Pulsar could be deployed very easily on Kubernetes with one single endpoint. There is a notion of Pulsar proxy, and proxy exposes one single endpoint, and that endpoint could be a service definition in Kubernetes, which in turn goes into a load balancer. And any connections can come through that single endpoint and goes through the proxy. Then that connection is forwarded to the broker without exposing the broker IP addresses explicitly. Especially in the case of Kubernetes, the broker addresses will change as the pods move around. So which means like proxy solves that actually. So now, when needed, the proxy could be completely isolated on a separate set of nodes, which are labeled, and that could be that endpoint could be exposed, so that the core nodes of brokers and bookies are completely separated out. So it's called aggregated deployment and segregated deployment. So the requirement 11, operability. System should be online and continue to serve production traffics in the following scenarios. Right? I mean, OS updates happen, security patches happen all the time, and failed disks are a reality. Then you need to swap those disks, and sometimes upgrading some of the software, like even the Pulsar system itself. So then the component should be self-adjusting in the sense like bookies turn themselves into read-only when 90% of the disk is full, and then when the network is kind of saturating, the brokers shift the traffic among themselves in order to shed some load. So these kind of operability, which are pretty automatic, was very attractive for this requirement on operability. Then the requirement 12 is disaster recovery. Since critical enterprise data flows through Splunk products, we need to make sure that we never, the system should be available 24/7, or in the notion of 4 nines to 5 9 capabilities. So customer expect continuous availability in the cloud and on-premise, required to handle data center failures seamlessly. Of course, Pulsar provides both asynchronous and replication and synchronous replication. The asynchronous replication is more attractive from a requirement perspective. Pulsar provides the capability to do either primary configuration or primary standby configuration that allows multiple Pulsar clusters to replicate data among themselves. And you can even control what data is being replicated, what topic is being replicated, and the producer and consumers on the second data center could be standing by, and we can, when we cut it over from primaries to standby, there is a capability called replicated subscription, which allows you to the consumers to pick up too close to where they left off. So, which is these capabilities are very attractive from a disaster recovery point of view. Then performance and TCO. Splunk application requirements are very varied. Some applications require real time, which is less than 10 milliseconds. The other application require near real time, which is less than a few minutes. And also like ability to handle multi-petabytes in a single cluster, which is a high throughput requirements. We did a complete detailed study comparing with Kafka. If I start going through those comparison performance slides, it'll be completely a talk of its own. So I've just summarized the results here. So Pulsar provides consistently 5x to 50x lower in latency for the 50th and 99th percentile. Pulsar uses 20 to 30% less brokers plus bookies, and it exploits available disk width efficiently. Then Pulsar uses 50 to 60% less CPU cores with complete control of memory. There's no need for grabbing memory out of page cache. Pulsar uses the memory only that you give. And Pulsar single partition throughput is 5x higher and 5x to 50x lower in latency. So in other words, Pulsar is 1.5 to 2x lower in CapEx cost, with a 5 to 10x improvement in latency and 2 to 3x lower in OpEx due to the layered architecture. That is the math that we concluded, which is very attractive from a total cost of ownership. Requirement 14, from an observability point of view, of course, when the system is in production, when there are issues that happens, we need to be able to pinpoint where the actual issue is. So from that point of view, system should expose relevant metrics, and it should be easy to get the logs and debug and troubleshoot. So Pulsar Observability provides tons and tons of metrics that ranges from system overview to messaging metrics, topic metrics, function metrics, and broker metrics, bookie metrics, and proxy metrics. These are related with the system, and it also provides log metrics, zookeeper metrics, container-related metrics, and the host metrics in which Pulsar operates to figure out where the issues are actually. Then Next requirement was the ecosystem, how broad the ecosystem is. Pulsar has been in the field for like close to 3.5 years now. So the ecosystem has developed quite a bit and is still evolving. But there is a decent amount of connectors and quite a few of the syncs also available, which satisfy that requirement. Then adoption, from an adoption point of view, we estimated around 600 companies, and it's still growing, and there is a lot of momentum behind Pulsar. And these are some of the companies that are already adopted, so that made this requirement satisfied. So in the community evaluation, from the community point of view, there is 280 contributors so far in the GitHub, and 30 full-time committers working in Pulsar in some way or other. And of course, we are the fortunate to have some of the Pulsar committers as well. And with the 600 plus companies adopting Pulsar, it's the system is battle tested, and the ability to fix any critical issues that this community has been always helpful. And we also looked at the GitHub stars, which is 5.7K, and it's growing. And licensing. So from a production point of view, we wanted to adopt an open source that is Apache license 2.0 and affiliated with vendor neutral institutions like either Apache and CNCF, and Pulsar obviously is an Apache associated with Apache. Avoid any vendor control components if needed. Then because of the fact that vendor could change the license later, once it's in production, it's very hard to take those components when the license changes. And so some of the people asked some questions related with what is the difference between Pulsar and Kafka. There's a bunch of differences that we evaluated. Durability perspective, multi-tenant perspective, tiered storage. Even though Kafka has added something on those tiered storage, but it's mostly on the closed source, not on the open source. Then geo-replication out of the box, and ability to operate the system in the presence of adding new nodes and deleting nodes, no rebalancing aspect of it, and lightweight functions integrated in Pulsar for computational purposes, support both queuing model and messaging models, and high throughput and low latency, and reduced total cost of ownership, and highly scalable aspect from a topic perspective. From we can take it to millions of topics when multiple teams are sharing the same underlying system. And recently, multi-protocol handlers have been introduced, which natively supports Kafka without any code changes, MPQ as well as MQTT. And of course, Pulsar's licensing is Apache 2. There's no vendor-specific licensing. And also, like in the OSS, Pulsar has several core features available as a single bundle as compared to collecting a bunch of components in other projects. So what did we do with Pulsar at Splunk? So so currently we have launched Apache Pulsar as a service running in production, processing several billions of messages per day. And Pulsar is integrated as a default message bus with the Splunk DSP 1.1 that was released on end of May, which is the core streaming product at Splunk. And Apache Pulsar is being introduced in other initiatives as well. Those initiatives, as they mature, then will be revealed at the appropriate time. So what is based on the Apache Pulsar at Splunk, I will zoom in on one of the products that our team is involved with, which is a Splunk DSP. Splunk DSP is nothing but a real-time stream processing solution that collects, processes, and delivers data to Splunk and other destination in milliseconds. And you have this bunch of data coming from application logs, market basket data, then mobile, and various other sources. Then you use Splunk Data Stream Processor allows you to filter, enhance, normalize, transform, aggregate, format, and mask sensitive data, and detect any anomaly detection patterns and conditions, and turn the raw data into more of valuable insights that you can infer on product sensitive data or even distribute data to other destinations like Splunk Index and data warehouse or even public cloud. So what is the critical challenges that it solves to the customer? So it gives control on the massive amount of data, which makes it hard to collect and product and deliver the right data to the right users at systems at the right time. And data visibility. Data-driven decision-making is challenged with multiple instances, like data being generated on the on-premise cloud and moving the data around to the appropriate place where you have to get the insights. Then generate business insights faster and to remain competitive in the data-driven environment. So the DSP architecture, if you closely take a look at it, we have a bunch of data collection tools in the form of Splunk protocols, which is called HTTP Event Collector for HEC, and S2S is a Splunk to Splunk protocol, which are data coming from the Splunk forwarders like Universal Forwarder and Heavy Forwarder. Then, of course, we can take data in a periodic fashion from other systems like CloudWatch Metrics, Azure Metrics, GCP Metrics, those kind of systems, and ingest data. And all the data ingested go into Apache Pulsar, and the stream processing engine takes the data from Pulsar, processes it, and routes it to Splunk Indexer and external systems. So Apache Pulsar is at the core of the DSP. So as a part of the closing remarks, Splunk is committed to advancing Pulsar as it's used by several core products and cloud services. And what are the work that we currently did in order to productionize Pulsar is improved Go client, then support for batch connectors. So far, the connectors in the open source has been based on streaming connectors where the data is continuously streamed into topics, whereas the batch connectors has the capability to run it on a particular schedule where the connector will be instantiated, then with appropriate credentials, then it goes to the source, collects the data, then shuts itself down. So that is the support for batch connectors that we have added. Then internally, we have added a Pulsar Kubernetes operator that allows you to deploy Pulsar very quickly and for the internal deployment purposes. And we have, since we have taken production with Pulsar, some of the critical bug fixes and other things that we have fixed. And so we have been very consciously pushing those fixes and some of the other features into open source to continue advance the open source as well as consume from the open source. Some of the feature work that we have planned include auto partitioning, then pluggable metadata stores, and enhancing the global state store so that it can be used at a high production scale. So that's all I had regarding why Splunk chose Pulsar. So I'm happy to take any questions since we have around 3 minutes.
Okay, great. Yeah, we have a handful of questions that came into the Q&A.
Not sure how many questions we can answer in the 3 minutes.
Probably just one or two, and we can take a note on the others. I'll leave that to you to decide.
Okay. So let me see, I can get to the question answer tab. Okay. How do I know which question to...
I see 7 questions on my side.
I only see the first, like, she can hear, I can hear the speaker.
Are you looking in the chat or in the Q&A?
Okay, I'm looking in the chat, I think. Okay. Okay, some of the questions I found out is, would be available Pulsar cluster or the detailed results of performance comparison with Kafka published someplace? If not, would you be able to share? So we will be writing a blog about it. From that perspective, there will be a lot of data that will be available. What are you basing your performance comparisons on? So the performance comparisons are they're based on deploying everything in a Splunk environment, and we did a clear apple-to-apple comparison. Performance setting, performance environment, all those details are completely available. If you want to know the detail a little bit, let me see if I quickly can share a screen. So this settings was done on AWS i38X large machines and with 32 CPU, 24 GB, and 20 instances with Pulsar tainted groups running 15 instances for running either Pulsar or Kafka, and Pulsar client tainted group for 5 instances for producing and consuming traffic. So essentially, we have done a complete evaluation, and all the data we'll try to write in the form of a blog. So hopefully that helps. Let me stop sharing the screen and get back to the questions.